I'm going to talk about probably a quick introduction and then get into the details, the guts of Aurora, under the hood. Okay. So, what is Amazon Aurora? We for a long time got requests from customers that, well, we love open source databases. We don't have to deal with complex licensing, software licensing cost, all the support issues and things like that. For that, you have to deal with commercial vendors. But we want something which is better performing and more scalable and available than typical open source databases. Say, okay, all right, this is a good opportunity here. So we started thinking about it, and it actually took roughly about four years, Sander?
That's right.
So to develop this. And what we have today, it's a MySQL compatible relational database engine. And when I say MySQL compatible, to be more specific, it's MySQL 5.6 and InnoDB compatible. Okay? But that's the most popular and the latest version, or 5.7 just came out, so still the most popular version of MySQL. And it has the performance and availability of commercial databases, but the simplicity and cost effectiveness of open source databases, right? And I'm going to get into the details of performance and availability, what we mean by that, and how we got there, right? Not just some numbers throwing at you, but also the architecture behind it. And it's all delivered as a managed service. Like I don't know if you guys are familiar with relational database service, the RDS service that we have in AWS, which automates many of the functions that typically DBAs have to do, like, for example, automatic backup, automatic point-in-time restore, right? So things like that are all included in the Aurora service. So at a very high level, and I'm going to get into the details of that, it looks like this, right? So we have a shared scale-out storage engine, which is distributed across 3 different availability zones. And that's where you get the availability from, because even if entire availability zone, which is essentially a data center in a metro area, goes down, you still have full availability. And then you have multiple instances. You have a single master, it's still a single master system, right, which does reads and writes. And you can have up to 15 promotable read replicas, which you can use as a master if the master fails. Right? And this is all automated, so you don't have to really do anything. If master fails, one of the read replicas will be available as a master. And it's also connected to other services like S3, for example, which we use for backup. Right? So we continuously stream data into S3, so you don't really have to have a backup window to do backups. It's all automated and happening all the time. Now, there are many reasons why Aurora is interesting, right? I'll talk about a few of them. Enterprise class availability. So one of the things we do in Aurora, and I'm going to get into more details about that, we do 6-way replication automatically across 3 different data centers, right? And then, in terms of failovers, if you have MySQL, you probably know it takes minutes, sometime more than that, to do failover. We can do failover in less than 30 seconds, right? And another very interesting feature, which is something I plan to discuss today, is near instance crash recovery. If you have been using MySQL, for example, you know that when database crashes and comes back up, depending on what kind of load you are running on that, it might take minutes, sometimes more than 10 minutes, half an hour to do crash recovery, right? Depending on when the last checkpoint was. In our case, because of the novel architecture, it's almost instantaneous. In terms of performance, we get up to 500K reads per second and 100K writes per second. This is, by the way, on a 8XL machine, right? So when you go to 4XL and 2XL, of course, you get proportionally lower numbers, but this is the highest we can get. And this is 5 times of what you get on a typical MySQL instance of the same size, right? Then other interesting thing is that the Aurora read replicas. These are low latency read replicas. And the replication lag between the master and replica is about 10 milliseconds compared to seconds, sometimes minutes in case of MySQL. And these are promotable read replicas, so each of them are doing reads at the same time. They're available to do writes when the master fails. And the storage in Aurora is very unique. In fact, that's probably the most interesting innovation in Aurora, right? One of the things which people like a lot because it's kind of easily available is up to 64 terabyte of auto increment storage volume, meaning that you start with a 10 gigabyte segment, and as you add more data, we automatically increase the volume up to 64 terabytes, okay? And you pay for only what you use. There is no provision IOPS that you need to pay for. IOPS also are billed per use basis. And as I said, it's a fully managed service. So a lot of the things like provisioning and deployment, patching and software upgrade, backup and point-in-time recovery, storage scaling and instance scaling, these are all automated through an API. So before I get into kind of the details of the architecture, let me give you a couple of customers who are using this. These are some of the customers who have been using Aurora: Expedia, GE Oil and Gas, PG&E, Art Networks, ISCS, United Nations, Alfresco, and if you haven't heard it before, this was actually announced in reInvent. This is the fastest growing service in the history of AWS, and now hopefully it will stay there for some time until the next one comes. So, couple of quick examples. Expedia, this is one of our first customers. In fact, they started using Aurora even before we officially launched. They were pushing us to, get permission to go to production even before official launch. You all know about Expedia, so I don't need to explain who they are. So the application they migrated from was actually running on MS SQL, Microsoft SQL Server. And this was a real-time analytics application, and this was essentially running out of steam because they have so much of data, and as you know in SQL Server sometimes if you have a lot of data, it kind of gets slower and slower. And they were considering various different options, right? They were looking at Cassandra because from the scalability perspective, that's pretty impressive. But they came to the conclusion that Aurora is actually a better solution for them. And they moved to Aurora, one of the very early customers, as I said, they're running happily on it. And they can do 25,000 inserts per second and a peak of up to 70,000 inserts per second, right? So they have been using this pretty effectively and very happy with it. PG&E, this is the large oil and gas company, not oil and gas company, electric company and gas company in California, right? So what they were interested in, they wanted a very reliable database which can scale very quickly when, for example, they have traffic surges. So what happens in their case, if there is a gas outage or a power outage, they have a lot of customers going to the website trying to figure out when the power is going to be back, for example, right? And they were very interested in the read replicas that we have, because in the steady state, they can run with a single master and a single read replica. And as soon as they have some spike in traffic, they can spin off more read replicas and very quickly increase the capacity of their databases and their website. And that's one of the use cases they're using it for, very happy with it. Alfresco, this is the largest, have you heard about Alfresco, by the way? So this is the largest open source document management company, right? And they have lots and lots of customers. They're actually now setting up a software as a service application on AWS. And they were running on MySQL. And they wanted to scale 10 times more than their current structure. And they are actually one of the big proponents of Aurora. And with the Aurora, they can scale to 1 billion documents and a throughput of up to 3 million documents ingested per hour, right? So another one of the customers who actually was so excited, they came to reInvent and talked about Aurora. Art Networks, this is kind of an IoT company, or this particular application is an IoT application. So they have 10,000 exclusive neighborhood level sensors for weather management at macro cell level or micro cell level, right? And their problem is that they have 25 terabytes of real-time data that they collect daily. And a lot of that data is actually stored in the databases. So they need very high ingestion rate. And they tried Aurora, and they are actually using Aurora as one of the production databases. Again, they moved from SQL Server to Aurora, and this was quite an easy move, and they, of course, saved a lot of money. So let me move to the next part. So I'm going to talk about two things, performance and availability, right? Just some quick numbers here. Some of you probably have, if you have seen Aurora presentations, you have seen these numbers. These are Sysbench benchmark numbers. Our write performance, this is on an 8XL with 244 GB of RAM and 32 cores. This is the largest instance that Aurora runs on today. Of course, you have plans to move to larger instances when they are available in AWS. So you get roughly about 100 plus K of write IOPS per second and 500 K of read IOPS per second, right? This is running Sysbench. All of you can run that. In fact, this is the way you can reproduce the results. We have a white paper on this because we get a lot of questions sometimes from people. Well, I tried to get this performance, I'm not getting it. And it's very well explained what is that you need to do. Somebody mentioned actually some client network bottleneck that you saw when you ran on Aurora. There are actually some network patches you can apply on the client side. In fact, that's what we do in the performance benchmark to make sure there is no bottleneck on the client networking side, right? So that's one of the things you need to do. In order to get to 100K writes per second, by the way, you need to have 4 8XL clients driving Aurora. Otherwise, you are not going to get to that level of performance. Other thing sometimes people make mistake of is that they run the clients in a different zone, availability zone than Aurora. And if you do that, network actually becomes the bottleneck and you don't get to 100,000 writes and 500,000 reads per second, right? So there are some interesting tips you have here. You can go and look at, it's actually on our website, that how to recreate the benchmark that we present everywhere. It was funny actually, InfoWorld, they wanted to try this, right? They set it up, and then they said that they are seeing 200,000 writes per second. And what happened actually, when you start the benchmark, sorry, go ahead.
I was just wondering, what's the monthly fee for that benchmark you're referring to?
The monthly fee?
Well, hourly or monthly cost.
So hourly and 8XL cost $4.64 in Virginia. And the prices are slightly different in other regions, but roughly about that range. So it's $4.64 per hour. Okay, and the lowest, the smallest instance you can get, which is large, that's by the way 29 cents an hour. Okay, so moving on, but
just quick question.
Yeah,
Are these slides going to be available? Can we put
yeah,
them on
I can send it
Okay,
to you.
great.
There are some notes in the slides. If I can send you a PDF, that probably will
Cool.
be easier.
Yeah.
I'll send that.
Maybe you can post the file right on the meetup site.
Yeah. We'll do that. In fact, I have given this talk at other meetups, and you can find it there also, but I'll send it to you. Yeah. So beyond the benchmarks, benchmarks are only so good, right? If all the numbers that you get in the benchmark is true in real life, life will be much simpler. Right? So why does benchmark doesn't quite work in real world? In real world, you have requests contending with each other. You have metadata which don't fit in the cache. You have data which doesn't fit in the cache. You have production databases which actually run in a high availability configuration. These are not single instances, right? So we reproduce some of these numbers with some of the scaling conditions. For example, we scale the number of connections, right? We scale the number of connections from 50 to 500 to 5,000, and we used Sysbench OLTP workload where there is fair bit of contention between different requests, right? And with 250 table. And we compared that with RDS MySQL running at 30K provision IOPS. This is, by the way, single AZ. And if you look at Aurora architecture, I'm going to get to that in a second, is that the Aurora is pretty much running in high availability configuration because of the storage architecture. And if you look at the numbers, the Aurora numbers actually scale up as you grow from 50 to 500 to 5,000. And the IOPS grow from 40,000 to 71,000 to 110,000. And in case of MySQL, it grows from 50 to 500. It kind of tops off at that level. And after that, because of the lock sharding and other kind of contention that you have in the database, it keeps going down and ends up at 13,000. And if you look at the best performance differential you get, it's about 8x. Now we also scale the table count to see how metadata handling scales in MySQL and Aurora. And we increase the number of tables from 10 to 10,000, right? And you look at Aurora, it actually went down a little bit as you grow from 10 to 10,000, but not by that much, from 60,000 to 54,000, which you would expect because now we have more metadata to handle. And we actually tried this on different types of MySQL configuration. We tried with RDS MySQL using EBS storage volume, which is kind of like network storage, right? SAN storage. We tried on MySQL using RAM disk. We tried on MySQL using local SSDs. And if you look at the numbers, well, it doesn't quite matter what type of storage you're using, whether network storage or local storage. There are some other things in the database which really is the bottleneck here. And it goes down from 25,000 or 18,000 in case of local SSDs, all the way down to 4,000 or 5,000 when you grow to 10,000 tables, right? We also scale the data set. This is trying to figure out when you don't really fit in the cache, right? If you look at the Aurora numbers, we increase the data size or data set size from 1 GB to all the way to 1 terabyte. And remember, this is running on an 8XL, so we have 244 GB of cache. So all the way up to 100 GB, it's actually fitting in the cache, right? And when you go from 100 GB to 1 terabyte, that's when you fall off the cache and you're hitting the storage and you're not getting all the cache effect, right? So as you can imagine, in case of Aurora, when you go from 1 GB to 100 GB, everything is in the cache, you're roughly about 100,000 writes per second, which is what I said. And with 1 terabyte, it goes down actually pretty significantly, but you will expect that because now you are hitting the storage, right? It's not all in cache. Interestingly, if you look at MySQL, the drop is really, really dramatic, right? It starts with 8,400, which is also very small. But when you go to 1 terabyte, it really goes down significantly. And the fastest we have with respect to Aurora is 67x faster. And we kind of were surprised because we are used to claiming that we are 5 times faster than MySQL, and this number was much bigger than what we expected. So we tried a different benchmark. We ran Cloud Harmony TPCC, which is a TPCC equivalent benchmark. We cannot really legally run the TPCC benchmark. And if you look at those numbers, it's actually even better, right? 136x or whatever the number is. So clearly there's something choking MySQL, which we have fixed, and I'm going to get into that shortly. This is running with read replicas, right? The HA configuration. One thing you see in case of Aurora, as you increase the number of write-offs on the master, which is generating more traffic for the read replica, the latency, the lag between the master and the read replicas don't really go up that much, from 2.6 millisecond to 5.38 millisecond. If you try that on MySQL, it can grow all the way from pretty much a couple of milliseconds to 300 seconds when you have really heavy load on the master. Right? Again, kind of shows the difference between the two architectures. So how do we do that? Right? This is probably more interesting than just throwing the numbers at you. So there are a lot of things that we do. There are 3 things I want to talk about. One is that we do a lot of engineering. And for example, we have done a lock-free implementation of the lock manager, right? This is a major bottleneck in MySQL. We also done a new thread model, right? We have implemented a much better version of the read query cache, right? But those are simple, not simple, but those are hard-nosed engineering. Architecturally, we have done two things which are very, very different. One is that we generate a lot less I/O than MySQL or traditional databases generate. And I'll come to that in a second. And the second thing we do, that we do a lot of processing asynchronously. So there is not one thread waiting for the other one. They do their job, wait for the response to come back so that you can use your cores a lot more effectively, right? Those are, I think, the two fundamental innovations in Aurora that I'm going to talk about. So in order to understand that, how we do that, it's important to understand the Aurora architecture a little bit, right? So if you look at a database stack, it is a monolithic stack that consists of SQL processing. This is really, the query processor, then transaction processing, caching, then you have a logging layer, then you have storage. What we have done in Aurora is that we have coalesced the logging layer and the storage layer into a single scale-out multi-tenant storage and logging layer. So what we have, if you look at architecturally, this is a single Aurora cluster. You have a single instance view, and then it is connected to a storage volume, a virtual storage volume we can think of, which splits across 3 different AZs, right? And for every data element, we have 6 copies of that, 2 in each AZ. And if you look at a larger cluster, you can add more read replicas. It kind of looks like that, right? But underneath this virtual storage volume that we have thousands of storage nodes. We have literally thousands of storage nodes, each with 8 SSDs, and we are doing a wide striping of data across these hundreds of storage nodes. But more interestingly, what we are sending to the storage node is not really the whole data pages. We are sending really the redo log records from the database instance to the storage node. To kind of explain it simply, we are not sending the dirty buffer pages when you write to a page. We are really sending the delta, the redo record, and the volume of that is much, much smaller than the data pages that you have to write if you have a typical storage volume which is doing either iSCSI or NFS or your typical storage protocol. So just to give you an idea, this is what the I/O traffic in RDS MySQL look like, right? So you have the primary instance where you are doing the write. That write goes to the EBS block store, right? This is step number 1. From there, it gets asynchronously mirrored to a EBS mirror because you want to make sure your data is not lost. Then you are doing a replication to the standby in multi-AZ, that step number 3, which goes to the other instance, the standby instance, which in turn is writing into the EBS volume it is connected to, which is also asynchronously mirroring to the asynchronous or EBS mirror that is writing to, right? So it's a lot of write that happens, and it's not only the log records. You're writing log records, you're writing bin log, you're writing data, you're writing into the double write buffer and blah blah blah, right? So net of this, we actually said, okay, this is all fine. So let's actually figure out how much I/O we do in order to run certain amount of transactions. So we ran sysbench, again on 8XL, for 30 minutes, right? And we got 780 transactions. And amount of I/O, this is the step number 1, by the way, not all the I/Os, I/O going to the first storage volume was 7.3 million roughly, right? So we are talking about 7.41 IO per transactions, right? This is only step one I'm talking about here. If you look at Aurora, what we are really doing is that from the primary instance, we are sending the redo log records to each of the storage nodes. Now, the amount of data in the redo log record, both the size of it and the number of records that we send is much smaller. But one thing which amplifies this is that since we have 6 copies of data, we are amplifying the traffic 6 times, right? But even then, if you look at, we did essentially the same experiments. We ran a sysbench workload for 30 minutes, and we got 27,378 transactions and 950K IO that we generated because of those transactions. It's roughly about 7.7x less than what we generated in MySQL, even with 6-time amplification because we are writing to 6 different storage nodes, right? So this is one of the primary reasons why our write performance is much better, because we are actually doing much less I/O than what MySQL or other databases using traditional storage engines. We do kind of a similar thing on the read replica side. So what happens in MySQL is that when you do replication, you are actually sending bin log from the primary to the standby, right, or the read replica. And when you send the bin log to the read replica, you're actually applying essentially all the writes that you're doing on the master, you're doing the same writes on the read replica also, right? So if you are, 70% of your transactions is write, then 70% of your transaction on the read replica are also writes, leaving you very little room, by the way, to do your read operations. What we do in case of Aurora is that we have a shared multi-AZ storage volume. So you don't really need to send all the bin logs, and we don't send the bin logs to the read replicas. All we do is that we send redo log records to the read replica. And if there is a dirty page in the read replica where the redo log needs to be applied, we apply the redo log to the dirty page in the read replica, right? So it's a much thinner replication stream, which kind of helps the performance of the read replica, and that's the reason the read replica performance is so much better. There are a few other things that we do. I'm not going to get into too much details. One is asynchronous group commits. An example of asynchronous operations that we do. We have an adaptive thread pool model, which is a lot more intelligent and adaptive in the sense that we actually increase or decrease the number of threads depending on the load that we have, right, which kind of helps also. And these are some of the other things that we do in order to improve our performance. Some of the things are still in the works. One of the areas, by the way, we don't do very well when you have to do, or do very well in the sense we are a little bit behind MySQL and traditional storage, is that when you do sequential reads. And we have a project in place. We actually have, we call it logical read ahead, because our storage architecture is very different. The storage driver do not quite know how to do sequential reads ahead of time by guessing what is going to be the next record that we want to fetch. And to mitigate that, we actually have a feature which is kind of in lab mode or trial mode now, called logical read ahead, but once we have that, it will be comparable to MySQL. That's one area where MySQL actually is better. One other thing I wanted to mention, all the things I talked about is throughput, right? You get a lot more throughput in terms of transactions per second. Our single query performance or latency is kind of similar to what MySQL has, because we haven't done a whole lot of changes there. We are working on query optimization, which will address that part. So you'll get much better performance even in single query performance. Okay? So any questions so far before I move to the next topic? Go ahead.
The question is your storage technology compatible at a level where you could integrate in the future future put Postgres database engine in front of it?
We could, yes,
Yeah.
we could. I mean, we haven't opened it up to general purpose storage, but for specific database storage, we can definitely do.
Yeah, just swap the engine, but.
Correct.
Cool.
Go ahead.
So right now you are compatible with MySQL 6 or 5.6.
Right.
What are the kind of longer term plans? Are you planning to stay compatible with MySQL
Yes.
like as they move to 5.7 and so
Yes,
on?
we plan to be compatible with MySQL 5.7, and as we grow, I mean, unless Oracle changes licensing agreements and stuff like
Is there
that.
right now some code sharing between the?
Well, it's open source, we can actually pick up that code. What we have done in the past is that, some of the features we have implemented ourselves. We maintain compatibility at the surface level, right? But the implementations are our own. For example, lock manager, we have completely rewritten to be a lock-free implementation. Query cache is completely different. Thread pooling is completely different. So when you get new features, for example, some of the things which are very useful, I think, in 5.7, for example, JSON support or special indexing, we would like to maintain we will maintain surface level or API level compatibility, but our implementations might be different so that we get better performance, for example.
So it's not like a fork of MySQL.
I wouldn't call it a fork. I mean, compatibility-wise, it will be same, but the code base will be different. I don't know what to call it.
Is Postgres officially in the roadmap?
I cannot comment on future roadmap. You will know it when you see it.
My question was more imaginative question, I didn't anticipate. I was curious how general you can be question.
Any other questions before you go?
What is support for replication across regions?
So Sandor actually is working on that. It's going to come sometime soon. So let me kind of give the answer that he was probably right. So today, for example, if you want to set up 2 clusters in 2 different regions and want to do bin log replication between them, and you can very easily do that. You can do it today, right? What we are working on that in order to start the bin log replication, you have to essentially do a bootstrap, right? And the bootstrap today is only MySQL dump and load. So we are going to do a storage level snapshot sharing and then an automated bin log replication setup so that you can do cross-region much more easily. So that's how we are working.
I'm curious what other vendors are doing that's close to this product. What other solutions are out there that you've seen
For Aurora? Or
Aurora?
you mean people using Aurora for other solution or other people doing something similar to Aurora?
What other vendors approach? What's the closest product that's going to be similar to Aurora? What are your other competition?
In cloud, I haven't, what we have seen most people do essentially support the traditional on-prem databases like MySQL, Postgres in open source world, and then Oracle and SQL Server in commercial world supported on cloud. Google has done Cloud SQL, for example, which is not quite like Aurora, but kind of a variation of MySQL, right? But I haven't seen something which is architected from scratch and optimized for cloud like the way we have done for Aurora.
Yeah, I would agree with that. I mean, even on the Microsoft stuff, it's the same sort of traditional thing. You put SQL on the cloud and off you go. I mean, I like the approach that you've optimized it for this environment.
Right. Okay. All right, so let's move to availability. Performance only matters if your database is down, right? And we have spent a lot of time thinking about availability, especially in the cloud world, where the architectures are different. And what we have come up with, and we talked about it a little bit in the previous section, is our storage architecture, which is 608 copy, right? So the way it is architected is that, let's say you have a storage volume of certain size, 100 GB, right? we chop that 100 GB into 10 GB segments, and then we make 6 copies of those 10 GB segments, put it on 6 different storage nodes, 2 each in each availability zone. And availability zone is really a data center within a metro area, right? The next 10 GB is going to spread across, go to 6 other storage nodes, right? So when you have a large volume, it gets distributed to a large set of storage nodes. And from the availability perspective, each of them is copied 6 times, right? That's where the core availability architecture comes from. And it is a quorum-based system. So in order to get write availability, you need 4 out of every 6 storage node respond to a particular write request, right? And by that time, you say, when you get that, you say the write is available. For reads, it's a 3 out of 6 quorum. Okay. Some of the other things that we do, that in the storage node itself, let's say, you're writing to 6 different storage nodes. One of them is down or slow for whatever reason, right? You cannot write to it. So there is a peer-to-peer copy that's going on between storage node. If a storage node thinks that it is behind its peers, it will do a peer-to-peer copy from other storage node to catch up. Okay. We do a continuous backup to S3. So we are not waiting for the backup window to happen. Whenever we write to a storage node, we are also sending the same log record to S3, and that essentially becomes our backup, and you can do a point-in-time recovery pretty much any point in the past by reading that log records from S3. We do continuous monitoring of all the nodes. So for example, if a storage node fails, we automatically replace that storage node with a new storage node, or bring it back up by rebooting it or whatever it is. We are doing continuous scrubbing of the data in the background, so that if there is issue, for example, in a particular drive, we reject that drive and then recreate those segments by copying from the peers, right? So there is a lot of background scrubbing that goes on. Some of the other interesting things about our availability architecture is, kind of pick some interesting examples, is instant crash recovery. So if you are familiar with MySQL, what you do is that you checkpoint, let's say every 5 minutes. That's a pretty typical checkpointing interval, right? And when the database fails, you bring it back up, and you go back to the last checkpoint, and you start applying the logs, right? Now, even if you have, let's say, 32 cores on your server, the log application, the crash recovery, is a single-threaded process in MySQL. So if you have a checkpoint which was done 5 minutes back, it might take 5 minutes, it might take more than 5 minutes. Sometimes if you are lucky and there is not too much of read, maybe it will be faster. But it can potentially take minutes, sometimes tens of minutes, for the database to recover, right? In our case, the architecture is very, very different. So what we do is that we are sending those log records from the database instance to the storage pages in the storage nodes. So when you come back up, all you need to do is to reboot the server, and the log records are already there along with the data pages in various different storage nodes. And when you need, or when you read a particular page, we apply the log record on the fly and create that page. So you don't really need to wait for your logs to be applied for tens of minutes, right, for crash recovery. And that actually gives us a lot of advantage in terms of failover times, because the recovery time is roughly about a few seconds rather than minutes. Other interesting thing we have done is survivable caches, right? So if you look at MySQL, the cache is actually part of the MySQL process. So we have taken that cache out of MySQL process. So for example, if you had to reboot MySQL D because you had a deadlock or something, you don't have to restart your cache, and your cache is already warm. That helps coming back up from a recovery very, very quickly. So if you add all of this up, instant crash recovery and all the other things we have done, and if you look at what is the impact of that in terms of failover, this is kind of a quick high-level comparison between what happens in MySQL versus what happens in Aurora. So in MySQL, let's say you have a DB failure, right? Then it takes some time to figure out that there was a failure. In our case, it's typically about 15 seconds, right? It can be lower than that, but we are working on that. Now, in case of MySQL, then the database comes back up, the recovery starts, and the recovery is kind of unpredictable, right? Depending on how much of log you need to apply from the checkpoint that you had before, that might take a few minutes. There is also a DNS propagation that's happening. What happens is that you failed over from primary to secondary. The IP address of the secondary now has to be propagated through the system so that the applications know where to go to, right? And that kind of happens in parallel. In case of Aurora, there are a couple of things that helps you. One is the failure detection doesn't really change. It's the same logic, although the team here is working on to reduce that time. But the recovery time is really, really short, right? Other thing that happens is that we have a driver. This is actually a MariaDB driver. MariaDB, if you have used it, you know that they have a driver for MySQL. And in the MariaDB driver, you work with them, and they don't have to wait for DNS propagation. They actually query the database to figure out who the new master is. So you can avoid the DNS propagation time. And the recovery in our case takes about 3 to 20 seconds. So in about 30 seconds, you are back up and running after a crash, which is pretty amazing actually. And by the way, like the way you can test all the things I talked about in performance, you can actually, using some simple SQL statement that you have added, you can try out the failover and failback and try it out for yourself. So that's all that I had. And if you have any questions, I'm happy to answer. Go ahead.
Yeah, just have a question. When you provision the service, do you have any kind of a management console that actually gives you visibility into your environment? Or do you have to use like Splunk or one of those other products?
No, we have a management console.
Okay.
So it's a fully managed service.
Oh, great.
You keep mentioning 3 AZs, 6-way replication. How about those regions where there's 2 AZs? Is Aurora supported?
No.
No?
So that's why, good question. I mean, that's why Aurora is supported only in regions where we have 3 AZs, although we are adding, third AZ in many regions. So today, Aurora is supported in IAD, Virginia, in Portland, in Dublin, and in Tokyo. But we are rolling it out in other regions as we add third AZs.
So you're
to
wait
those.
for AZs, you're not going to try to backport Aurora to work on it?
We currently don't have that plan. We are pushing our colleagues to have the third AZ in other regions.
I'm all for it.
What's the limit of restores? Is it 31 days?
Sorry, say that
For
again.
backup and restore, is it 31 days?
How long do you retain the data?
So I can answer that one.
Go ahead.
You can set your window anywhere from 0 up to 31 days. And we retain as much as you want us to set. Yeah, so what that means is we give you a daily snapshot every day that you can say, I want to restore to this snapshot. Or you can say that you can pick any point in time in that window and say, down to this second, I want to restore to that point in time. And another nice thing I'll add, since you asked that question, is because of the way the storage, we'll come to the front so people understand. Because of the way the storage system is architected, restoring is actually a lot faster because a lot of that work happens in parallel. So you can restore back to any point in time with a very large volume. Let's say you had a 6 terabyte database, you could basically restore that in under an hour. Whereas for traditional databases, that would take hours, maybe even days in some cases. So there's really a lot of benefits that we weren't able to get into with Aurora. The fact that there's backups going on continuously behind the scenes without any performance degradation, and the fact that you can quickly restore to any point in time.
Can you restore to an alternate server?
Yes, you can. Yes, I can say I want to spin up a different database based on this current database. Absolutely. Yeah.
Go ahead.
Compliance, PCI, DeFi, if that works?
So not yet. We are working on HIPAA and BAA and FedRAMP, and we are looking at PCI also. There is, in terms of technical work, there is nothing left. We have to go through
You
the
mentioned multi-tenant storage. This is what triggered my question.
but it is all encrypted.
Okay. So it's a matter of going through the audits and getting the
Correct.
controls. It's not a matter of technology change.
No.
Okay.
Go ahead.
I wanted to ask about cache invalidation since you removed it from the system. Is it possible to have a cache hit on stale data?
No. I mean, you might, the read replicas are behind by 10 milliseconds, right? So if you're talking about that staleness, that might happen. But as soon as we get the redo records on 30 pages coming to the read replicas, we apply them or, essentially drop that page from cache. So you're not going to read wrong data. You may be stale by 10 milliseconds, which is the replica lag.
But there is no staleness when I fail over from the writer to the reader, right?
No, because it's the same storage volume.
Okay. Yeah.
So at the storage level, it's the same data. But when you have, the two of the master and the read replica, the caches could be different. That's what he's asking.
Yeah.
And we are 10 milliseconds behind, so you may be reading data which is 10 milliseconds behind, but it's not, wrong data.
I know you're not going to be a fan, but do you want to talk, would you mind commenting on the timeline for when you're going to go multi-region?
Multi-region in terms of the replication,
Yeah.
it should be this quarter.
Thank you.
And if it doesn't happen, you can go and harass Sander.
Well, and to add to that, this is something that you can set up on your own today by doing the logical dump and load.
Right.
But what we're talking about is doing a managed solution for you so that it's just a one-click operation.
My question is more different. So 4 years ago when this was being dreamt up, how many of these improvements or what were the basic tenets of the improvements that you wanted to achieve, and what was just, what results came as just surprises that you got that were, because it's a pretty amazing, fleet of different improvements that you were able to achieve. Like how many of them were actually engineered versus surprises? Yeah.
So let me start with, this was the first. Our goal at a kind of strategic level is that we wanted to have commercial scale performance and availability, right? But the open source attributes in terms of cost and simplicity, right? We didn't know at that time what kind of performance we are going to get, right? So, there are two teams, one team working on the database engine, another team working on storage. And, the database engine team kind of did very well, came up with good performance, and the storage team did very well, came up with performance. When you connected the two, performance was terrible. And we didn't know what kind of throughput improvement we are going to get. And it took a long time, a few months, to figure out what is that we need to do to optimize the performance of the end-to-end system. And for example, the 5x, we didn't know for a long time whether it would be 5x or something different, right? But the fundamental tenets, and it is still valid today, that the performance and availability of commercial databases with the price and simplicity, or cost and simplicity of open source databases, that's kind of drives us.
And so did you have any expectations on terms of performance? Was there any mandate or any idea on like, well, it has to be 5 times better or 10 times better?
Well, we had an internal compass that we want to be 5x better, right? But if we will be reaching 5x or not, we didn't know for a long time. Go ahead.
Question here. So you talked about single primary or master scenarios, and what use cases would you need to have, like multiple masters, and like what else would you change if you need to have?
Well, I mean, for two things. One is availability, right? With multiple master nodes. For example, today when you do a failover, you essentially take a 30-second hit, right? Which is okay for most application, but with multi-master, you won't have to take that, right? Other thing is write scaling, right? To the single master, although 100,000 is plenty of writes for most applications I know of, but if you have multiple master, you can scale that also. Any other questions? So by the way, Sandor has some Aurora gift cards.
I do. I have some $50 Aurora credits if anybody wants to take it for a free trial. Giving those away, just come and see me. And Alexi and Dimitri also have them, so feel free to talk to them as well.
All right, go ahead, Mike.
Because the storage is HA, by nature, you don't have to worry about data loss. If you're running a single instance, how long is the failover time if it has to move to a different AZ?
It's what?
So I can talk about that. It depends what type of failure you're talking about. If it's a failure where the database process has crashed, then it's going to come back up within 5 to 20 seconds, as the budget was saying. If it's a situation where the hardware has failed, you could be talking about up to 5 minutes, because what we have to do is basically spin up a new host in a different availability zone, get everything set up there and running, and then propagate the DNS. So you're going to be talking about 5 minutes instead of 30 seconds, which, you know, to some applications that's acceptable, so you can cut down on cost by only having a single server running. But if you can't afford 5 minutes of downtime, then you're going to want to provision multiple servers in different availability zones.
I actually would like to add something to it, because since this is, so if you run a single instance, it's the provisioning of a new one can take 5 minutes, but it's a little tricky because in case of an AZ failure, we do not actually move your instance to a different AZ. So you're still encouraged to use at least one replica in different AZ. That's one thing. And another thing is it's hard for us to detect failure if we just cannot reach to a particular server. So the failure detection in multi-AZ case is much more aggressive than in single AZ case, right? Because we don't know, maybe it's our internal network has problems, right? So we don't want to shut down the database and like move it somewhere.
But in case of Aurora, though, we also monitor the progress on the storage side, right? That if the LSN is moving,
yes,
then we know that there is activity going on and it is still up.
That's right.
Even for a single AZ.
Are you measuring, have you got CloudWatch metrics or any other metrics or other third-party tools that are
Right, good question.
working with Aurora?
Good question. But we do have CloudWatch metrics, and we recently added 50 new metrics for Aurora as well as MySQL and MariaDB with our advanced monitoring feature, which just came out. And with those, you can monitor more metrics either on the RDS console or through CloudWatch. And you can also integrate those CloudWatch streams into third-party monitoring systems like Graphite or AppDynamics, whatever have you.
And does that allow you access to query execution times?
Not query, these are mostly system level, but there are some query execution type metrics, but not very many. We are planning to add those, but the system level metrics are there.
Actually, when you call it system, it's engine level, right?
Correct.
I'm wondering if you can list any other cons to it, like why I might use, any reasons I might use RDS over Aurora for MySQL.
Well,
I think you mentioned sequential reads might have been a problem.
That's not a reason not to use Aurora. I'll tell you some of the reasons why you can still think about MySQL, right? By the way, Aurora is also an RDS engine, so you don't really say not use RDS.
Okay.
It's really a compare between Aurora and MySQL, right? So, what we tell customers that if you are in an availability zone, if you are in a region where Aurora is available, and Aurora is supported on R3 instances which go from large to 8x large. And if you need an instance which is large or larger, then use Aurora, right? There is no reason really to use anything other than that. Okay. No reason to use MySQL. If you're in a region where Aurora is not there or needs something which is smaller than R3 large, then MySQL is a good option for you, right? The other reasons you might think about using MySQL is that, let's say you have a global architecture, right? And you want to have the same engine everywhere. And Aurora is not there everywhere yet. MySQL may be an option. But we strongly, if you look at the feature function, the performance, availability, and cost is something I didn't talk about. In terms of cost, it is also going to be cheaper for you because you're not paying for provision IOs. You're not paying for multiple storage volume. It's a single shared storage volume for all your instances, right? There is no reason to use MySQL.
Okay, thank you.
All right, so who is going to go and try Aurora after this talk?
Yay!
All right. So somebody had a question. You had a
Well, I mean, just quickly on the global architecture side, is Aurora something that could be positioned ultimately to support that global architecture?
Yeah, that's what we are kind of,
Yeah.
doing essentially, right? I mean, we rolled it out in the 4 important regions that we have, and we are going to gradually roll it out to other regions.
And so for a general right layer.
Correct. Okay.
Well, I just want to say congratulations. I mean, it's an amazing engineering feat in terms of taking, something like open source MySQL and then applying it to the best of what the cloud can deliver. Really cool, really exciting, and really amazing. So we're in awe of what it can do. So very cool. Well done.
Thank you, and thank you for all of you.